Hey guys, it's Mr. Wolf and we're back with another video for Unit 6. Today we're going to be talking about area and sectors. I will be honest, this is probably the shortest video you'll have to watch for the unit, but that doesn't mean that it is any less important than the ones you've watched so far or the ones you'll watch in the future. Once again, if you guys missed something, make sure you pause, catch up, rewind, rewatch, whatever it takes, and make sure you're filling out those guided notes. If at that point you still are confused on anything, you can reach out to me or Mr. Rose and we'd be more than happy to help you. So let's just jump into area. Area is something I think you guys should have definitely heard of at some point in time. Maybe not with circles, which is what we're going to focus on today, but I'm sure you've heard of area. With that being said, let's just go ahead and refresh ourselves on the definition of area. So the area is the measure of what is within the bounds of a shape. So the measure of what is within the bounds of a shape. That's a very technical definition, precise, but I think one of the best ways to think about it is it's just this area right here, this shaded region we're looking at, which of course I'm not going to be able to shade in every last bit, but it's just the inside of a shape. Whatever's within that shape, that space will be your area. And you guys may have done this with different shapes before. Let's use this square as an example. Let's say we had a length of 2 and a width of 2, our area would be 4, right? Then if we add this measurement on a triangle, we'll say this is 4 and this is 3 down here, this base. You could say, well, to get the area of a triangle, it's height times the base over 2, so we end up with 12 over 2, which is 6. And this is just review. You guys don't have to worry about this or writing it down. But this is kind of a review of what exactly area is. And it's important to remember these things when you dive into using them on new concepts, because you may have not necessarily forgot what it was exactly, but how precise things are and whatever it may be. It's always important to review. But today, we're going to be focusing on the area of a circle, which we've looked at a few things for a circle. We've got the radius, and we've looked at the diameter, and we've looked at chords, and we've looked at the circumference, which is the measure all the way around. So we've looked at a lot of different things with circle, but one thing we have neglected to look at is the area. So let's investigate the area of the circle a little bit. So without just giving you a formula, let's think about what we could do to get the area of a circle. We don't know how to do it right now, but let's think if we could take this circle and turn it into a shape that we do know. So let's slice it up. Now we have 1, 2, 3, 4, 5, 6 slices, and let's pretend that these are all even size slices. I know it's not the best looking thing in the world because it's free-handed, but you'll have to forgive me on that. So now we have these almost triangular with a little bit of a curved edge shapes. Let's see what this looks like if we move them around a bit, pull them apart. So let's say we have one here. We stack another beside it, that's 2. Then another, that's 3. And another, that's 4, 5, 6. And this isn't the most beautiful thing in the world, but you can see we have a slanted line here, and then these lines that come around like this. This should look familiar as far as a shape. Let me show you something maybe a little bit more precise. It should look something like this. Actually, we'll turn it this way. Oh, it's not turning. Okay. Something like that. Of course, we've flipped it around, but you can see how we would get this if we just kind of gave it a little bit of a rotation and dropped it down here. Transformation, if you will. That should be a word you guys remember. So now we have something like this, and let's draw our shapes in here. We got first piece here, and then, oops. This one's a bit slanted compared to the one I drew, a bit more slanted. But we have this, and this, this, and that gives us 1, 2, 3, 4, 5, 6. That last line here. And this isn't perfect, but basically what I'm trying to say is if you can break these up, you can get them into a shape we know, like the parallelogram, which we focused on a lot in the last unit. So if we look at this and think, okay, well, these longer sides of the parallelogram are built of the curved edges of a circle. How long could those be? Well, we do know that the curved edges, if you add all of those up, that's going to equal the distance around the circle, or our circumference. But we need to remember that this is divided up into two. Half the curved edges are on the bottom, half of them are on top. So whatever the circumference is, divided by 2 is going to be either of your bases. Okay, well, what is the circumference divided by 2? Let's think about what we use our formula for, a circumference. So circumference is equal to radius times 2 times pi. And if we wanted to get circumference over 2, let me extend this page a bit, we could just divide both sides by 2, right? So we divide both sides by 2. Now we're left with the circumference divided by 2. And over here, we have cancel out our 2's, and we're left with radius times pi. Well, okay. Maybe that gives us something with a little bit more insight. Let's erase circumference over 2 and change these radius times pi. Now, what do we do here? How do we get the area of a parallelogram? I'm not quite 100% sure if we covered this as far as the area of a parallelogram goes, but I will say this. Similar to how we did with the triangle, we need this height value here. Something along the lines of that in order to get our area. So we need to look back and remember that, hey, this parallelogram we have is built from this picture right here, which is built from slices of the circle. So what would the distance be from any point on this bottom line to the center of one of those slices? Well, let's look. This bottom line we said is just part of the outside of the circle or the circumference. So we'll say, let's start here. And then it goes into that center point. Or you could start here, go into that center point. And what do we know about that line segment? Something that connects from on the circle to the center point. Well, that's just a radius. So this height here would be our radius. So let's think. What's the formula for the area of a parallelogram? Well, the formula is base times height. So if we wanted the area of parallelogram, so we'll write this, area of parallelogram, that would equal radius times pi. Well, since this is all multiplication, we can just go ahead and drop those parentheses. So we'd have radius times pi, which would equal radius squared times pi. So we started off with a circle, we sliced it up, turned it into a parallelogram, figured out what pieces we needed to get the area of that parallelogram, and ended up with this formula. And it just so happens that that is the formula you need to get the area of a circle. I'll give you guys just a second to copy any of this down or take it in a bit further before I erase it. Okay, erase some of this. Clear this out so we can focus on the circle now. Okay. So, we said just a moment ago that the area of a circle is going to be equal to our radius squared times pi. And remember, guys, I know you guys probably know this, but just a little note, radius squared is just equal to the radius times the radius. So in this case, say we had our radius is equal to 4. Then we could say, well, our area is going to equal 4 squared times pi. Well, what's 4 squared? 16 times pi. And just like the circumference problems, you can leave this pi in the answer. We can leave it at this, 16 pi. You don't need to multiply that out in the calculator and round the decimal. You can if you want. You'll still get a correct answer. It'll just be rounded and not as accurate. So this is the best way you can put the answer, and this is how I would recommend leaving them. So let's do a couple more examples before we move on. Just to kind of pound it in your guys' heads. Hopefully you won't forget this. This time we'll draw the radius out. So say you're given a circle that looks like this, and it says the radius is 6. Well, okay. I know that area is equal to radius times 2 times pi, or radius squared times pi, apologies. So area is going to equal to 6 squared times pi, which equals to 36 times pi. So we can just write it as 36 pi. Not bad, not bad. Now let's try something a bit different, not quite different, something just a teeny bit different. Let's say you have a diameter, so your diameter is equal to 14. Well, now what do? We need radius, right? You guys should remember that diameter is equal to the radius times 2, or you could say that the radius is equal to the diameter divided by 2. So if we want the radius, we can say, well, 14 divided by 2 is equal to 7. So 7 must be our radius. So we plug that in. The area is equal to 7 squared times pi. So the area is equal to 49 pi. And hopefully those examples cleared that up. You're going to definitely have several problems like these. But honestly, if you know that formula, these aren't bad. So make sure you keep this formula burned into your brain, because that is a very important one. Now let's talk about a sector. A sector of a circle. This is something you've actually seen and worked with without actually knowing that you've seen or worked with. A sector of a circle looks something like this. And you think, well, isn't that just a central angle with an arc? It is. This is the arc out here. And this is the central angle, starting with this point and going up this way and down this way. But this whole region, this shaded region that we'll try to color in some, this area right here is what we call a sector. So I remember when I did the video for arcs, the first thing I did on arcs is I used the piece of pizza example as how we could find an arc. You slice the piece of pizza and you end up, that crust line would be your arc. Well, think of the sector as the entire piece of pizza. It's that whole area within, not just the outer edge, not just the angle. It's the entire area of that slice of our circle. I know that's not the best colored in, but that whole area, I think you guys get the gist of this. So let's give a definition. Sector is a region within a circle bounded by the central angle and intercepted arc. So I think we kind of broke this apart already, but let's look at it again. The area, or the region within a circle bounded by the central angle and the intercepted arc, is known as a sector. So you have your central angle, that's one side, your arc is another side, and that second half of the angle there, kind of bound it in, create its own little shape, its own little slice of that circle. So there are 3 major things that you need in order to find a sector. And let's think about it. Remember when we did arcs, minor arcs, and major arcs, one way we could find a major arc was by saying, well, if I have the minor arc, I know that the whole circle is 360 degrees. So if I need the major and I have the minor, I can subtract the minor by 360 degrees and we get the major. Well, this is very similar, except with area. So if we want to find the sector, we have to first find the area of the circle. This way we know how much the circle is at a whole. The entire area, these extra regions out here, not just the sector we're looking for. So once you know the whole thing, you have to find out what fraction of the circle does this sector cover. So we have to know how much of this sector right here is the circle. If I said, well, that's 1/4 of the circle, you would know that it's 1/4 of the circle. And then you could say, well, if the whole circle is 12, I can say that if this is 1/4 of 12, then that would be 3. Talking about area, of course. And then the last thing we do is just what I said. Multiply the area of the circle by the fraction. So let's review this. You find the area of the entire circle. That way you know what you have as a whole. You figure out what fraction of the circle that sector covers. So how much is that sector covering? Then once you have that fraction, you multiply it by the area of the entire circle. So these are 3 steps to find the sector. Very important. Now, let's have a formula for this. The area of sector is equal to the measure of arc AB in this case. We'll call this AB. So AB. And remember, those letters may change, but this is what we're working with from here. Divided by 360 degrees times pi times our radius squared. At this point, there are 2 questions you should be asking yourself. How do we find the measure of AB, that arc? We know what we can get in degrees, like how big it is in degrees. We've done that a ton, but we need to find a measure. Also, how do we use pi times radius squared? What exactly does that mean? Well, if you remember from just a slide ago, pi times radius squared is our area of a circle. So this is our area. And this is something we need to find. And let me clarify upon something I just said. I made it kind of seem like we were looking for something different on the arc for AB, but really that's what you're looking for. We've done that a lot. But we need to do this fraction. We found arc measures and subtracted and added depending on what we need to get. But now we're building a fraction here, and I'll explain why. We need a fraction to figure out what fraction of the circle is this sector. Well, if we know what fraction the arc is of the 360 degrees that makes up this circle, we know the fraction that this sector takes up. So let's just say that our central angle, we'll say angle ACB equals, let's go with something like, this looks like a right angle, so let's just make it a right angle, 90 degrees. Okay, well, if our central angle equals 90 degrees, then we know that arc AB is equal to 90 degrees, right? So then we have really all we need, except for the radius. We do need the radius here, but let's go ahead and plug this in. We know that 90 degrees divided by 360 degrees, that's our fraction that we needed, times pi, because you always got to have a pi in there, times radius squared will give us our area of the sector. Now, when you do these, you will be given the radius. So in this case, we'll just say that we have a radius of 6. Why not? So then we plug in our 6. We say 90 degrees over 360 degrees times pi times 6 squared will equal the area of our sector. Well, 90 over 360, that can be reduced, and that will help us to figure this out without having to use a calculator. By all means, use a calculator if you need one, but I think it's always best to do math without a calculator if you can. I won't make you do that right now because I'll just go ahead and tell you that 90 over 360 reduces to 1/4, because if you multiply 90 by 4, you get 360. So we have this fraction left here times pi times 6 squared, which is 36. Well, then we can combine what we have left to get an answer. So this pi, we always like to leave the pi, right? So let's leave the pi here and just deal with these two. So 36 times 1/4, well, let's write it like this at first. Let's say 36 over 4 times pi will be our answer. Then we can reduce that fraction, right? 36 divided by 2 would be 18. 4 divided by 2 is 2 times pi. And oh, wait, look, we can reduce it more. 18 divided by 2 is 9 times pi. So our answer is 9 pi. Of course, this work may have been a bit slow for some of you because I know you guys probably looked at that, thought, well, 36 divided by 4 is 9, and you got to there, but I like to break these things down as much as possible. Let's do another similar example. Let's erase what we have here. You know what? Let's just add a new page. Save ourselves some time. Let's say the arc AB equals, let's do 70 degrees. Let's just plug in some random numbers here. Our radius is equal to 12. And we need to get the area of the sector. We can draw our circle too, just to make sure you guys know what you're going to be looking for on what kind of problems. So you'll have a circle like this. You'll have your center point that comes out. You'll have an angle, points A, B, and of course your center point. Looking for that shaded region again. We also say that our radius is equal to 12. So you'll have a problem like this, something like that, and you won't be given this part over here. You'll just be given this circle, and from that you have to find the area of the sector. So we remember back to that formula, we know the area of our sector is going to be equal to AB over 360 degrees times pi times our radius squared. Okay, well, we can start plugging stuff in. We know that AB is equal to 70 degrees. So 70 degrees divided by 360 degrees times pi times our radius squared, which is 12. Get that square. So then we're left with this. 70 degrees over 360 degrees. Oops. Times 12 squared, which is 144, times pi. And I moved these two around just because we always like to leave that pi alone. So don't worry about that pi. If it comes out in the middle, it comes out in the middle, but you can always push it to the end when it comes to a step like this. So then we just got to reduce our fraction and multiply, and we're good. So let's take the same slow steps we did last time to reduce this fraction. Makes things a little bit easier. Oops, not mean to do that. Okay, so the first thing we do here, one thing I like to do with reducing a fraction is we just get rid of the 0 on the end. So 70 over 360 is the same as 7 over 36. We times our 144 times pi. And then 7 over 36. I don't think that reduces anymore. Now all we do is multiply, and you would get 252 over 36 times pi. Well, if you'll look, our fraction now has two even numbers, so we can definitely reduce that down. This would equal 126 over 18 times pi. And we still have two even numbers, so we can divide that by 2 again, and we get 63 over 9. Then we sit, wait, can that reduce? Ask yourself, I'll let you guys come up with an answer. Can this reduce? Well, let's say this. 9 times what equals 63? 9 times 7. So what we're left with is 7 pi. Hopefully this makes sense to you guys. Let's break this down one more time. We have our central angle at 70, which means our arc AB equals 70, and we're given a radius of 12. We say that that arc measure divided by 360 times our formula for the area of a circle will give us the answer. So we're left with 70 over 360 times pi times 12 squared, which gives us 70 over 360 times 144 times pi. We multiply our 144 on top, giving us 252 over 36, and we eventually reduce that down to 7 and have our pi still there. Remember, guys, you don't have to put that pi in your calculator. Pretend like it's not there, but do not forget to write it in your answer. That is very important. It looks like the video lasted a little bit longer than I expected because I wanted to give you guys some good examples. The notes for this are very short, so make sure you guys do every bit of those notes you can. And for those of you who actually listened this far into the video and didn't just skip around, I really do appreciate that you take the time to listen this far. And once again, if you drop your name in the bottom of the page near where your last answer is, you'll get a couple bonus points for watching this far. Thank you guys for paying attention and doing so good this unit. You guys have stayed caught up for the most part, and I very much appreciate it. The test is coming up quite soon, so make sure you're studying these things. Make sure you've got your guided notes all completed and correct. If you have any questions about whether your answers are correct so you know what to study, feel free to ask me or Mr. Rose, and I will quit rambling on and let you guys get back to whatever it is you need to complete. Thank you guys again, and I will talk to you soon.